Before we get into the presentation, just very quickly, like everybody does about me, I'm a software developer and a consultant. I've got a long background in doing information and document management back in the day. I founded Network Planet in 2004. We developed a bunch of commercial tools, but I've also been working on open source projects, particularly at the intersection of .NET and Microsoft technologies and RDF. So I'm currently lead developer on .NET RDF, which is a library and toolkit for working with linked data and RDF in .NET. And I also developed Brightstar DB, which is an open source RDF triple store. Again, all written in C#, all written in .NET. My company, Network Planet, we do software development and consultancy, strangely enough. We developed a whole bunch of commercial products, always standards-based, from ISO standards through to W3C standards. We've tried to bring those into the workplace. Our current focus, though, is on helping third sector organizations with the challenges of dealing with open data and with linked data as well. So the agenda for today is to talk about a service that we have just made available called Datadoc. So I want to start off by talking about the motivations that drove us to create Datadoc in the first place. And then we'll do a little bit of a walkthrough of how it looks from a user perspective, and finally talk about it from a technical perspective, what happens in the background. So Datadoc really came out of this sort of like the driving concern that we had about publishing data, and that publishing data really shouldn't cost the earth. It should be something that's available to organizations of all sizes, from big companies right down to individuals with something that they want to publish. So Datadoc is attempting to address some of the hurdles to publishing linked data by providing, first of all, a free service. It's a cloud-based service building on top of existing infrastructure. So we're building on top of GitHub and GitHub pages, which gives us a great deal of scalability. Because it's built on top of GitHub and you're publishing your data via GitHub, it's all within your own repositories, so you have complete control over your data. You own your data at all stages. And because Git gives us all of these wonderful features of diffs and change history and that kind of thing, you get all of these things kind of feeding through to your data publishing processes, along with some magic that we provide, such as converting CSV to RDF for you, making your static pages actually work as linked data so that IDs can be dereferenced and turned into real data, and doing things like automatically updating links to data dumps for you as you update your data. So you may have seen this infographic if you've ever worked in the open data space, where there's five levels of open data, or 5 stars of quality of open data, where you can get 1 star just for publishing your data under an open license, so just for actually making it open, regardless of what format it's in. 2 stars if you've managed to do something in a machine-readable format. 3 stars if that's a machine-readable and open format, so CSV rather than XSL. And then 4 and 5 are kind of reserved for doing the linked data stuff. So for 4 stars, you actually use URIs to name the things that you want to talk about. And for 5 stars, you link to other people's URIs, so you're kind of connecting yourself into the web of data. So what we found is that there is this hump at the 3-star level, where many data publishers who are considered to be good examples of open data publishing are basically stuck at the stage of publishing CSV spreadsheets. And they're spending a lot of time, money, and energy on data publishing platforms that host this 1 to 3 star quality of data. So I'm thinking about here about national government, a lot of local government data portals. These are all kind of at this level. And in a sense, the data is out there and it's available for people to use, which is a good thing. We can't take anything away from that. But it does mean that there are certain challenges for you as a data consumer, particularly the need to have to download entire spreadsheets of data in order to work with just a piece of that data. Now, some of those are very small data sets and it's no problem. But if you want to get the postcode lookup file, it's hundreds of megabytes zipped. And by the time you've actually expanded it out onto your disk, you're going to have to buy a new machine. So another challenge that comes along with that is that people tend to just convert their XSL to CSV, stick it on the web, job done, they walk away. Which means that you end up with column names that you don't know what the column actually is containing. You don't know what the original data types were because, of course, all of that stuff's got lost. You've got no idea if they've used a controlled vocabulary in this column or not. So you have a lot of problems when you just grab CSV and try to work with it. And, of course, because these are all different organizations or different parts within organizations, there's no consistency in the way that they name columns. There's no consistency in the way that they reference the things that are contained within columns. So you have very difficult challenges when you're trying to combine this data, especially if they're coming from different sources. But as I say, despite all of that, people are like cheerleading the fact that at least the data is out there, which is true. But we do seem to be stuck at this hump where 3-star CSV is considered to be high-quality open data. And I'd kind of argue that it's not. And I think that the argument is kind of beginning to go my way. So this is a quote from the International Open Data Roadmap. Just making data publicly available can no longer be the beginning and end of a conversation about open data. The focus of the movement is shifting now to building open data communities. So the question then is, what does an open data community really mean? Well, obviously it means a group of people all coming together around data. But I think that it also, in a networked environment, it means making the most use of the tools that we have available to better collaborate with people that we're maybe never going to actually meet face to face. And the web is this huge platform for collaboration. So making our data work better in the web is one way of enabling this data collaboration to take place. But even when you talk to people who get it, and people who really want to do the linked data thing, there are a bunch of hurdles that they have to overcome. So one of the main hurdle is a psychological one, which is just that you get hit with a whole bunch of terms, a whole bunch of standards that you need to sit down and or you feel like you need to sit down and read. You need to understand what URIs are and why they're important and how you're going to, then you've got this like free space in which you can create all of these identifiers and it's like, how am I going to get started? And so that tends to lead to this sort of like analysis paralysis sort of problem where you just don't know where to start. So it's easy just to publish a CSV and walk away. So we would say that we need to have processes that are very easy to enable you to get data out there and to get feedback on it and take a leaf out of the open source developer's handbook, release early, release often, get feedback, make changes, go from 0.1 to 0.2 to 0.5. To 1.0, yeah. But actually do that process. And a lot of data publishers don't consider themselves to be inside of that kind of loop because it's difficult for them to make changes and to change their processing pipelines. The second thing is around, like, there are just a huge number of standards and in some senses competing standards sometimes, and the great thing about standards is there are so many to choose from. But especially when you get to trying to produce 4- and 5-star linked data, there are a whole bunch of things that you need to take into consideration. So one of the things we want to do with Datadog is to take that bit away from you. We'll let us worry about that. We'll generate valid void metadata for you automatically. We'll make sure that your data is at least 4 stars, and will help you to get to 5 stars. And the third thing, especially when we're talking about charities and smaller organizations and individuals, is the hosting infrastructure. Okay, so going to a GoDaddy or somebody and getting a website hosting is pretty straightforward. But if you want to do linked data hosting, you've got a whole bunch of stuff around content negotiation, hosting RDF files alongside your HTML files. And that can be kind of difficult to get your head around what you need to do. So we wanted to fix that bit as well. So from a user perspective, I'm going to just quickly walk you through, didn't do a demo, I'm just going to quickly walk you through some pictures of the site. So this is the Datadog.io site. As you can see, you can log in with your GitHub ID. So I'm going to take you through the process of actually adding data, assuming that you've created an account, and connected to your GitHub ID. So once you've connected your GitHub ID, you can basically choose any of your public repositories as a data repository, as a Datadog data repository, and you can publish your data into it. That includes any ones for organizations that you belong to. So we're enabling people to actually come together as a community, decide to create an organization inside GitHub, and then contribute their data to that organization. So having chosen where you want to go, you then select a CSV file from your disk, from your local disk, and go through a few stages where you're asked some questions. Most of these things you can just clickety-click all the way through. There's very few bits that are actually required for you to stop and do any thinking. This is the only page really where you need to do any thinking at all, where you need to give a title and a description and choose the license for your data. So we give you a set of different open data licensing options. So this is like your very basic metadata that you provide about your data set. Datadog will then attempt to sniff out what data types you're using, your CSV is actually using on a column-by-column basis. And it will do that the best it can, and it will get it right about 80% of the time and get it wrong about 20% of the time, but you can correct it and tell it what data type it really is. And if there's particular columns that you just don't want to appear in the RDF, you can suppress those as well. Then what we do is go to the RDF stage, and this is the bit where if you don't care, you can just click straight through, and we're choosing some relatively sensible defaults for you. We will by default generate a URI for all of your columns, for the property names, if you like, for your columns, based on your dataset repository, its ID inside of Datadog. So it always appears under the datadog.io domain because we can serve the linked data from there. But if you want to, you can override that. For example, might want to say that we want to use the FOAF vocabulary for our organization column. We also allow you to choose how the identifiers are generated. So again, by default, we're basing identifiers off of the CSV file name and the row number within that CSV, which, it's kind of just some kind of default to get some identifiers out. But obviously, if your CSV already contains some unique identifier column, then you can go ahead and just use that. Then magic happens. There's no screenshot of magic happening, but magic does happen. And eventually, a data set will pop out. So the data sets, as they are processed, we index the metadata. And so that will drive things like your dataset list page on your own homepage, but also search to be able to find things. I'm just going to show you, actually, I've got other screenshots. So this is one of my accounts with some data. And these are my data sets. You can see some of the processing jobs that have been done. Search at the moment is relatively basic, but it's mostly tag driven. We're planning to sort of extend it as we go along to be a bit more full text based. But at the moment, you can search for things by according to what they're tagged by, and we've got a few data sets that are related to Bristol because my colleague Jen lives in Bristol. We have documentation. Yay! Thank you. And this is what your published data actually ends up looking like. So this is the page for a resource. So it's Shibuya Station in Tokyo. And this is linked data that has been generated out of my CSV that I uploaded. So we've got the properties down here. These are all using my own definitions, which, as you can see, you probably see really small letters down there, are basically IDs in my own namespace. And all of this stuff just works as linked data that I can browse around and download the NQuads as well. So obviously, if I wasn't using a browser, if I was using an application, I can also just make a request for this ID and ask for NQuads in the accept header, and all of that stuff happens automatically as well. I should say as well is this is my GitHub repository that's actually driving that data. Okay, so I'll talk about what's in the different folders in a minute. So back to the presentation. So yes, pages I didn't show you. So this is actually, so every repository, every dataset repository that you create gets its own void description. So void is a vocabulary of interlinked datasets. So it's basically a vocabulary for dataset metadata. So you'll get a void file that describes your dataset repository and all of the datasets that it contains. And then you'll get another a void file for each of your individual datasets. So in addition to having things like the title and the description that you entered, there's stuff that we automatically generate, like a count of the number of triples in your dataset, links to the data dumps for the dataset, links to example resources, and so on. So all of that stuff is just done for you automatically. And there's a different entity you can see. So behind the scenes. This is kind of like the high-level architecture for Datadog. We run everything, as you might imagine, because we're a .NET-based company, is that we run everything in Azure. All the conversion stuff is all done in the cloud. We use Cosmos DB on Azure, which is like a document store to drive the search and to drive some features of your dashboard. The actual work of turning your CSV into RDF is done as a batch process. So we have a bunch of worker threads that are sitting, waiting for new jobs to come along. And what they will do is they will deal with the data that you've uploaded, but then push all of that data into your GitHub repository. Okay? And it's pushing it into your GitHub repository and then using GitHub pages to actually provide all of that data. So we're pre-generating all of the pages for your site, all the HTML, all the RDF is just getting statically generated and stuck into your GitHub repository. And then that's served up through GitHub pages. It's a really scalable way of doing the publishing side of things. But because, of course, everybody's GitHub pages site is going to be under the github.io domain, and it's not going to do content negotiation and all that kind of stuff. So we have a front end, which is just load-balanced Nginx servers that are just doing content negotiation and redirects, so that datadoc.io domain IDs will resolve either to HTML or to NQuads, depending on your accept headers. So that's pretty much all there is to it. Conversion process itself is just a pipeline. So the inputs are the CSV that you've uploaded and the CSV metadata, which is just a JSON file. And that contains the manually entered metadata like your title and description, but also all of this column mapping and data type information that's needed in order to generate the RDF. So it runs through the pipeline. The first step is just to convert your CSV into RDF, and then to further process both the metadata JSON file and also this generated RDF in order to generate the void metadata for your data set. And then those two bits of information, all of your RDF and the metadata RDF, get put into an RDF data store. Okay? We'll talk about the RDF data store in a minute. But that data store is part of your GitHub repository. Once the data store is updated, then we go ahead and generate the static files. Now, because what we're doing is generating the static files for all of the data sets in your repository, we actually go through and we just run through your entire repository. That means that when you have a resource that is actually referenced in multiple data sets, all of that information gets brought together for you in one place, which is what you want. So the output all goes into, as I say, all goes into your GitHub repository. We don't hold on to any of it. So you have 4 folders, CSV, which contains your most recent CSV files and the accompanying metadata. We're using the CSV on the web metadata standard for representing that data, which means that actually this also works as a CSV and CSV on the web repository if you want it to do that. We have the data. Data folder contains all of your linked data that's been generated as NQuads files. So each individual resource has an NQuads file. And the page does the same thing, but in HTML with RDFA embedded. And finally, there's a directory called quints, which contains the raw RDF data. So this is actually the RDF data store, the persistent store for your data. Every time you do a commit that results in a successful transformation, we then tag your GitHub repository as well. and attach a release to it, and that release contains a zip package which has the RDF data that you just created as a result of that conversion. Okay, so lots of different ways of getting hold of your data. So the RDF data store is one of the interesting bits of what Datadog is doing. As I say, we wanted a way to be able to persist all of the RDF data that you've got in your data store, but to be able to do some querying and merging on it automatically. Quince is basically a big RDF index that is all file-based. Indexes are basically built based on the MD5 hash of the subject or predicate or object, depending on which index we're doing. And then the entries within the index are N-quads. They're the full RDF data for a particular quad. One of the problems that you have if you've ever tried to do this stuff with RDF is that you end up with this, at one end you could either have like one really big file with all of your RDF in it, which is really hard to process and Git doesn't like it. And at the other end you could have lots and lots of small files with all of your RDF data in it in different places, which is really hard to process and Git doesn't like it. So we wanted to have something that's kind of in between. So we came up with this dynamic partitioning scheme where as files grow, they split and gradually migrate into a deeper and deeper hierarchy of directories, which I'll show you. Thing about Quince is there's no server, right? It's just files. So it's just plain file access. We open sourced our implementation of it, which you can get from GitHub as well. So this is a way that, our object index, which allows you to find any quad according to the object part of the triple, starts off its life just as a file called _o.nq. And we start inserting data into that file. So these files are just lists of N-quads. They're kept in sorted order, so you can do a quick binary chop type search through the file itself. Eventually, that file is going to get too big, and it reaches a threshold point. Once it reaches a threshold, what we do is essentially split the file. So we replace the file with a directory instead, and we re-index the quads that are contained in that file. And we're re-indexing then based on the first byte of the MD5 hash for the object. Okay, so this will end up with up to 256 files inside an _o directory, and the _o.nq file just gets deleted, goes away. And eventually, those files are going to get too big. And so when one of those splits, we then re-index on the second byte, and so on and so forth. So as we're adding more and more data, essentially our data files are moving further and further down, essentially a sort of a B tree. And it's just a really simple tree index. So the nice thing about this approach with Quince and especially with Git is that the two things work together. So all of our files are N-quads, and N-quads as an RDF format is a line-based RDF format, which means that you have like one line in the file is one quad. Yeah. So Git's default diff algorithm is a line-based diff, which means that we can track changes at the quad level. So we can tell actually, you inserted this quad and deleted this quad. So in the case where a commit has simply inserted into files and no files are split, you just take the git diff. Try saying that. You take the git diff, and the git diff between two commits is simply, that's the list of inserted quads and deleted quads. Even when an update has caused a file to split, it's really easy actually to work out what's the result of simply the re-indexing and what's the result of actually new data, because a re-indexed quad will be both inserted and deleted. Okay, so we can do real simple set algebra in order to work out what was actually added and what was actually deleted versus what changed because files were re-indexed. So one of the things that we are excited about with this approach is that we have this persistent data store now, which works like a little index. It works like a searchable index of all of your RDF data. And there is this really simple linked data RESTful API proposal called linked data fragments. So the whole of the API is based around this idea that you can ask for all quads which match a filter, where I can specify the subject, the predicate, the object, or one or more of those things, and get a list of all of the triples that match. So in Quince, that's really easy for us to sort out. We can simply find the index file in the appropriate index, filter on the remaining parts of the query, and return the matches to the user. So it's really simple to do. So we're planning to actually implement that as a web service that will sit kind of like alongside our Nginx front end, possibly just done in Python actually. And it will use the static site that's published by GitHub Pages and just do that small amount of filtering that is necessary in order to serve back the quads. So that gives us a form of query, a really simple, basic form of query. What becomes really interesting is there's this client-side library called sparkle.js, which is a JavaScript implementation of the Sparkle query language for RDF. And it uses linked data fragments as a way of getting the pieces. Basically, it decomposes your Sparkle query into a bunch of linked data fragment requests, and then fires them off at the servers that you want to query. So we actually had this, suddenly this ready-built client-side distributed query facility, which will enable anybody to come along to the datadoc.io site and query across all of the data sets that we know about. So that's going to be really cool once we've got it done. So just in summary, datadoc.io is a free service which implements a very simple RDF generation and data publishing. We're using GitHub at the back end for persistence of both your source data and also the converted RDF. We're using GitHub Pages because that gives us this scalable, fully cached publishing infrastructure. And we're also using that Git store as a way to persist our RDF data in quite an interesting way. And we have this potential for supporting distributed Sparkle query. So please do, if you have any data publishing requirements, please do check out datadoc.io. We'd be really happy to hear about your experiences of using it, get suggestions for any ways in which we can improve it, because we're really looking to carry on developing it actively. Check out Network Planet, networkplanet.com. I also have the privilege of presenting the linked data track at the XML Summer School this year. So it'll be a fun 2 days full of learning about linked data and all of the related technologies. And yeah, you'll all be very welcome to come along to that. Thank you very much.
Thank you very much, Cal. Any questions?
So is CSV your only input format?
Currently, yes. It's trivial for us to add RDF formats as the input format, which will be something that we're planning to do. We'd be interested to know about other people's requirements for other forms of data input as well.
A couple of things. One, having ingested your CSV file into Datadog, what do you do to update your data if you found a typo or want to add something? Yeah. And second, if you've published some data that isn't linked to the wider semantic web, but could be, it's got geolocations in it, do you have a service to then attempt or support making those wider links?
Yeah. Okay. So on the update side of things, yes, the way that updates work at the moment is brain dead simple. We've tried to keep everything brain dead simple. If you upload a CSV file with the same file name, we replace the old data. So if you fix the typo, don't change the name of the file, it'll just essentially overwrite your data. Sorry, I'm going to some blank. Second part of your question was about the linking to the wider semantic web. So at the moment, when you have a column that is recognized as being a URI, we will say, do you want this to be an actual link out to the web? And then we'll take that. So you can format your columns in that way. But we realize that's not really a useful way of doing things. So one of the things that we wanted to do is to actually start to learn a bit from the data that people are publishing, and to try and work out, sort of in the machine learning way, to try and learn a bit about what would be a suitable link to suggest for this data. So if we have something that, this looks like a postcode, or this feels like it might be a county name, to suggest ways in which we could link that data across. But that's going to require some volume of data to actually have some data we can actually test with.
You mentioned of 80% of the time it is the conversion is good, and 20%. So if we are converting a big document or a lot of huge document, it is then become questionable where the 20% will lie. Is there any way, any tool you have that can give some idea, or otherwise, manually going through is impossible?
Yeah. Yeah. So the 80-20 rule is around correctly detecting the data types in the column. So you can always override that manually. But even then, there can be quality issues inside within a column itself. You might say this is integers, and then suddenly you find there's some text in a column, something that breaks the integers. So there is another service which is actually run by the Open Knowledge Foundation called Good Tables, goodtables.io, and Good Tables is a way of doing that sort of verification of your CSV based on it attempts to do some data type sniffing. They're a little bit more advanced than ours, and it'll attempt to check that you're consistent throughout your columns. But you can also provide it with a schema that says my data should look like this. Please verify it. So one of the things that we plan to do is actually take their technology and integrate it into ours. So that then it can just be part of that processing pipeline. Once you upload the CSV, we can go through and check. And especially if you're doing the update and you're actually saying, okay, I've just corrected this thing, you've already gone through and said what the data types in the columns are. So we want to actually just take that schema and validate that you haven't added a new column or changed around the schema, so we can actually validate against the previous version of the data that you've got.
Thank you very much, Cam.
Please ask